quick, because what I really want you to see here is the range of oscillation, the parts of it, the specific details of an oscillator. What I want you to pay attention to here is energy, the motion variables, force, and time. Those are the things I want you to pay attention to in this diagram. Right. The first picture there is the system in equilibrium. Nothing has happened to it. It's just resting. The system in equilibrium has a net force of 0 and does nothing. But this also represents the relaxed position of the oscillator, meaning this is the point where there's been no stretching or compressing of the spring, so we know the force from the spring is 0. That's identifying what I would call the equilibrium position of your oscillator. And if this were me, I would just draw yourself a straight line to indicate that you know that there's an equilibrium position for all of these. So I'm going to put it right in there, right on top of the map. So that's our equilibrium position. This first thing is t equals 0. The start of our oscillator begins when we displace the oscillator, pluck the string, initiate the air column, or in this case, pull the spring outwards a little bit and let it go. This is supposed to be the moment that you let it go. So you're not holding it in place. There's no hand holding it there. We have pulled the oscillator to the side some distance, which we will call x max, because this is the amplitude of the oscillation. This is maximum displacement. It's the furthest our oscillator will be displaced from equilibrium. At t equals 0, when you first let it go, the velocity of your system is 0. And at this moment, your force is at a maximum, because x is at a maximum. So you experience maximum force at time equals 0. So if you're actually riding a ride that does this, this would be very dangerous, because you would let it go. It'd be like whiplash. You'd get all the force all at once. So you don't design rides like this, because this also means the acceleration is at a maximum. Right? If force is at a max, acceleration is at a max. Force and acceleration are always linked together. Because the velocity is 0, the kinetic energy is 0. Right? Velocity is 0, there can be no kinetic energy. But this is a spring mass system. And because it's a spring mass system, it has elastic potential energy, which means at this moment, the elastic potential energy is at its maximum because x is at its maximum. So we say at this moment, all the energy is in the form of elastic potential energy. Okay. All right, we allow a small amount of time to pass. So t is greater than 0. Now, at this moment, t is greater than 0. It's less than 1/4 of the period. Now, to understand why I chose 1/4 of the period, zoom out for a minute. Do you notice that this is just 1/2 of an oscillation? I go from one side to the other side. I don't make it back. So an oscillation, you have to come back to where you started from. So this is just 1/2 of the oscillation. I say that because that means at this point, this is 1/2 of the period. Period is a time for one oscillation. That also means in the midpoint between these two, this has to be 1/4 of the period, so it's 1/4 of an oscillation. So this is the quarter, and this is the half. We only have represented half of an oscillation. So going back to here, we're looking at the time between when we first release it, but before we've made it to equilibrium. This is the time between 0 and 1/4 of the period. At this point, the object has moved to the side, so it has developed some amount of velocity. Right? It's been accelerated. It was experienced the maximum acceleration for a few moments, and it's been still accelerating to the left. So the acceleration is this way. Its displacement isn't at x max, but it has some displacement to the right. Now, direction is important here. The displacement's to the right, but you'll notice velocity, acceleration, they're to the left. They're in the opposite direction of the displacement. So the object has sped up, but at the same time, the force is no longer a maximum. The force is something less than that. X is smaller, so the force has gotten smaller. And it also means that because this equals ma, the acceleration is some amount related to x, but in the opposite direction. So if x to the right, the acceleration is still to the left. It has some elastic potential energy because the spring is not at zero. But it also has some kinetic energy because the object now has some velocity. But nothing took any energy out of the system. So this sum still equals whatever we started with, 1/2 k x max squared. Oscillators conserve energy. So the total energy that we added to the system, what we started with, is now split between kinetic and potential. This represented the amount of energy we had at t equals 0. All right? Paid attention to time, acceleration, velocity, position, energy. It's all here. We're going to go to the next part. Now we've made it back to equilibrium. Now at equilibrium, x is equal to 0. Now there's some implications here. The object's still moving. It has a velocity this way. This is the velocity of the object. But if f equals 0, if x equals 0, then at this moment there's no force on the object. And if there's no force on the object, there's no acceleration of the object. So as it passes through the equilibrium point, it's neither speeding up nor slowing down. But that also means there's no elastic potential energy. This must mean that the kinetic energy is at a maximum. And that must mean we have a maximum velocity. When it passes through equilibrium, it's going as fast as it's going to go. Its maximum velocity is when it passes through equilibrium. I said that twice. Don't you say it a third time? Maximum velocity is when it passes through the equilibrium position. Now, if you're really paying attention, you'll be able to note that that must mean that the amount of kinetic energy is going to be related to how much potential energy we started with. These things have to be equal. The energy didn't go anywhere. So how far you pull the mass out has a direct effect at how fast it will be traveling through equilibrium. If you want to travel faster, pull it out farther. If you want your guitar to be louder, pluck the string harder. Right, same thing. Ready to keep going? New time. We are now at a time greater than 1/4 of the period, but we're less than 1/2 of the period. We're in between. You'll notice suddenly that the displacement is on the other side. Velocity is still in this direction, but it's getting slower. And the reason it's getting slower, force equals minus kx. If x is on the left side now, then the acceleration has to be this way. And that's because the force is also this way. You're starting to push in the spring, so the spring is pushing back. The spring is trying to keep the object at equilibrium. But the object has inertia, so it passes through equilibrium and keeps going. But the force, the acceleration is all back towards equilibrium. Now, I can do all these things, and I will. That's still true. There's elastic potential energy. Doesn't matter what side it's on because the position is squared. There's kinetic energy. Doesn't matter what direction it's going because the velocity is squared. And these two still have to add up to be equal to whatever energy we had at the beginning. All of that's still true. That's all the way until you reach this point. Here, we're back at the amplitude. We've made it to the halfway point in the period. So at this moment, we are at X max. So that also means the force is maximum in this direction. We're just on the other side. So we must be at maximum force. Because we're at maximum displacement. That also means at this moment, maximum acceleration. Because we're at maximum displacement. But also, velocity is zero. All the energy is back in the form of elastic potential energy. There's no kinetic energy. So our energy is all back 1/2 k x max squared. There is no kinetic energy. And we have done half of a rotation. Or half of an oscillation. So, energy, x, va, force and time for each one of these. And I don't want to do this because I don't have enough space here, but this whole thing just repeats as you go this direction. Right? We'll get back to an equilibrium. This equilibrium is at 3/4 of the period. When we get back to this side, this is at 1 period. I want to spend a few minutes talking to you about why we are going to study this. First, one of the things I said from the beginning is that we say something's in simple harmonic motion if it obeys Hooke's law. And then I had you do a lab specifically on a spring mass system so that you could see something that dealt with Hooke's law directly, a spring and a mass. And you did a pendulum lab too to see that something has similar function with a mass on the end of a string. What I want you to understand is that we study the spring mass system because it is the basic idea of an oscillator. But there are a lot of things that oscillate. What we try to do is see if our system that is oscillating has features like a spring mass oscillator. Because if it does, all of the results from studying the spring mass oscillator can be applied to that new system. So I'll say that again. We're going to come up with a set of results. Results that we believe are all based on a system being a spring mass oscillator. Things like that the period equals 2 pi times the square root of m over k. Now, figuring out where that comes from in all of this is not straightforward. It's not easy. And I just want you to be kind of understanding that the math is a little bit beyond the scope of this course. But it should have some clear indicators as to why the numbers are where they are. Like, you may not be able to figure out why there's a 2 pi here. That might not make any sense at all about why 2 pi exists here. But it should be pretty obvious why the mass of the oscillator is up here. If the object were heavier, would it be easier or harder to move it? Harder. It'd be harder to move it. Will it take longer to move it or less time to move it? Does it make sense now why M is up in the top? Now, K is how strong the spring is. Right? How strong the spring is. Let me ask you this. If the spring were stronger, do you think it would pull harder on the mass or pull with less force on the mass? It'd pull harder. Do you think it would move it faster or slower? So if K is in a denominator, it would move faster. It would take less time to oscillate. Do you understand why those are where they are? Now, math will prove why there's a square root function in there and why it looks the way it does. But it should make some mechanical sense about why the spring mass system looks like this. Now, there's more to it than that. You also spent a little bit of time with the pendulum oscillator. This one might be harder to see, so let me remind you of a few things. The function that we're looking at here was L over G. Now, this just looks tough, I think. Like, where is the logic in L being in the top and G being in the denominator? I can't do all the reasons why, but follow along with something for just a minute. Would you agree that it's gravity that's probably causing the pendulum to oscillate? Like, if there is no gravitational force, do you think the pendulum would oscillate? Let's take our formula here and just multiply top and bottom by M. That way we get mg in there. Because does it make sense to you that if the force were greater, that it would oscillate faster? So if I pull down harder on the pendulum, I would expect it to oscillate faster. And so mg in the denominator makes sense. Does it make sense to you? But the ml in the numerator still doesn't make a whole lot of sense to me. Until you realize that a pendulum is rotating, right? It's rotating back and forth. It's not moving in a straight line back and forth. So this would have to be a torque, not just a force. If I multiply top and bottom by L for the torque arm length, this now is a unbalanced torque. And do you recognize what the top is? If not, I'll tell you what it is. The top is the inertia for a point mass, ml squared. Does it make sense that the inertia of the object is in the top of the fraction and the unbalanced torque is in the denominator? That if I have more inertia, it will take longer to oscillate. And if I have more applied torque, it'll take less time to oscillate. So although L over G doesn't look like it, all oscillators are going to have a feature where their inertia is going to be in the top and whatever's causing it to oscillate is going to be in the bottom. More importantly, all oscillators should have some kind of restoring force that models this proportionality. Now again, Mr. Shelton, why are we bothering? Well, because you want to pass the AP exam and because I want you to pass the next test. There's always that. But I hate teaching on the idea that, well, you just need to pass a test. Oof, Mr. Shelton, you can do better. No, you can't. Does it look like something? Is it an okay? Can you at least go with it? So anybody who's ever played on one of these, I'm just going to put one string on our guitar. Is that all right? Who's played a guitar or any kind of stringed instrument? All right, so I have enough of you where this should work. And since middle school made a lot of you try stringed instruments, I know some of you have this idea. So remember, we're trying to figure out maybe how this works and why these are the way they are. So a guitar has 6 strings, correct? Have you ever noticed that some of the strings are thicker than other strings? So this should be easy. The strings that are thicker, do they make low notes or high notes? So the thicker strings make lower notes. That means they oscillate slower. Does that make sense? The period of oscillation would be a bigger number because they oscillate slower. Where do you think the thickness of the string goes? Numerator or denominator? If it was thicker, it would be more inertia. It would oscillate slower. So, do you think the thickness of the strings is related to the mass? Or do you think the thickness of the strings is related to how much force there is? What do you think? Is this too hard to understand? So where do you think the thickness of the strings would go? Numerator or denominator? Top or bottom? See, I think this is hard. I've heard both top and I've heard bottom. I'll say it again. Thicker strings, high notes or low notes? Low notes means the period takes a long time. Low note oscillates slowly. So if I want the period to oscillate slowly, do I make the string heavier or lighter? So I must have the mass at the top. That's where the thickness of the string goes. Now, anybody who's played a string instrument knows that you probably can adjust how fast it oscillates by changing something about the string. What's something you can change about the string? So there's something that will increase or decrease the tension. So if I increase the tension, does it oscillate faster or slower? So if you make it more tense, does that note go up? Or does that note go down? No, it goes up. When you increase the tension, the note goes up. So that's what's down there. If I increase the force, it oscillates more quickly. The period becomes a smaller number. A guitar string is a simple harmonic oscillator. It obeys all the rules for simple harmonic oscillations. There's something else that probably has an effective change too, and you guys might not have said it yet. What else could change how fast the guitar string oscillates? Most likely that would play into the density. Something simple though. Who's played the guitar?
The thing you strum it with?
If anybody who's played the guitar knows you can change what sound the guitar string makes by something simple. Yes, sir?
The leg, by changing the leg.
Yeah, you put your finger down somewhere, and suddenly the guitar string plays a different note. You have changed the length of the string. How do you think all these musical instruments work? Obviously, we have very few people who play guitar. So perhaps we need something that is more so I got a reed at the top with the reed thing on it, and there's lots of holes and little buttons. So a single reed instrument. So anybody playing band understands that your woodwind section has a variety of single reed instruments. They are all more or less based on the same principle. The concept that all of your devices that oscillate are going to oscillate on a principle where the top part's going to have to deal with how much inertia there is in the oscillator, and the bottom part's going to deal with what it is that is causing a force to act on your oscillator. If you can identify those things, you can predict what controls the oscillation. I would not bring all this up except that you saw in your last test something that looked like a kid finds an equation on the internet. Does it make reasonable sense? Does it agree with what you thought would happen? Could you imagine one that had to do with a guitar or a clarinet? Because I can't. These are the kinds of questions I think would be fairly straightforward to think about, because they will definitely look at something like this and ask you if you realize, does this make reasonable sense? So